Okay, AP Chemistry. This is the answers video part 2 for day 50, Rate Mechanisms 3. And so we're going to go ahead and continue with problem 14.63. All right, so what is the molecularity of each of the following reactions? Write the rate law for each. So molecularity has to do with how many different types of compounds or molecules or ions are involved on the reactant side. The fewer there are, the easier it is for the reaction to take place. So if we look at A, the only thing that's going on here is you have a chlorine molecule hitting other chlorine molecules and breaking apart into two chlorine atoms. So that's called unimolecular. Uni means one. When you have two different compounds, ions, or atoms striking each other, that's called bimolecular. And the following is also bimolecular. You have two different types of atoms, compounds, molecules. So it's more difficult for a bimolecular reaction to take place because you have to have just the right combination, in this case of the OCl and the H2O breaking apart, recombining, or in this case the NO and the Cl2 breaking apart and recombining. Even more rare are ter-molecular, T-E-R molecular. That would be three different atoms, molecules, compounds that would have to strike and break apart to recombine. So that's a very difficult reaction to take place. So that does not happen very slowly. Okay, so unimolecular, bimolecular, ter-molecular. Okay, it says write the rate law for each. So since it says these are elementary reactions, it means that we can use the coefficient as the exponent in the rate law. So this one will be, of course, writing the exponent 1 is optional, but the exponent is 1. All right, the next one would be these two. And exponent's also 1 because the coefficients there are 1. And finally down here. All right, and that takes care of 1463. Okay, we'll move on to problem 1468. It has 4 parts to it. So the decomposition of hydrogen peroxide, H2O2, is catalyzed by the iodide ion. The catalyzed reaction is thought to proceed by a two-step mechanism. And you see, there they are right there. Okay, write the rate law for each of the elementary reactions of the mechanism. All right, so we'll start with this one. We'll do it over here. Only involves these on the reactant side. Okay, so the coefficients are 1, so the exponents will be 1 as well. And then for this one, we'll write it over here. Okay, coefficient's also 1, so we'll put the exponents as 1. Okay, so those are, again, you can use because they are elementary reactions, you can use the coefficients as the exponents. All right, write the chemical equation for the overall process. So we're going to use Hess's law, basically, and do this. So look for something that only appears once in either of the reactions, and we see that the O2 does. Only appears right here, nowhere else. So we're going to come down here. We'll draw our arrow right here. So the O2 is going to be on the right side, because it's on the right side of this arrow. It doesn't appear anywhere else. Okay, what else? Anything else? Nothing else does. So now we can start either adding or canceling. Again, the same rules as Hess's law back in the thermodynamics unit. So let's look around. We have an ion on the right side of this arrow and on the left side. That means they're going to cancel out. So I'll lightly draw a line through those two. All right, I'll also draw a box around O2 to mean that we actually used it and we're done with that. Okay, also the iodide ion right here on the left side of this arrow and over on the right side of this arrow will cancel out. Okay, and now we don't have anything else that'll cancel. So on the right side of the arrow in both reactions we have H2O. So that means down here we're going to have 2 H2O. We're going to add those together because they're on the same side of the arrow, the right side of each arrow. Okay, so we've taken care of those. And over here we have H2O2 and H2O2 both on the left side of their arrows. So we're going to have 2H2O2. And that reaction should look familiar. That's our elephant toothpaste reaction. Hydrogen peroxide breaking down into water and oxygen gas. So identify the intermediate, if any, in the mechanism. Okay, so what we had here is IO minus appear at the end of the first step, and IO minus being completely consumed at the beginning of the second step in the second step. So that is an intermediate. Okay, so IO is an intermediate because it is produced at the end of the first step right here, and at the end of the first step and consumed in the second step. So it doesn't appear at the beginning of the first reaction, it doesn't appear at the end of the second reaction. It's produced and consumed within the reaction. That's the definition of an intermediate. Okay, assuming that the first step of the mechanism is the rate determining step, predict the rate law for the overall process. Okay, so slow step, fast step is the easy situation. That's the easier of the two. That's the one we illustrated out on the lawn, because what happens is these products of the first step are produced very slowly. And as soon as they're produced, they're automatically, the IO minus is gobbled up right away by the fast step, the second step. It takes this just a few of these come out here, and this is a fast reaction down here, so it picks up that IO and immediately processes it to finish the reaction. So this one is the simple one. Everything that's produced here is either just going to stay in solution like water, or the IO is going to immediately be processed with more of the hydrogen peroxide to produce these final products over there on the right. Okay, so that means that the slow step, the rate law for the slow step is going to be the rate law for the overall reaction. So the slow step is called the rate determining step because the overall reaction cannot happen any faster than the slowest step. Okay, that's going to determine how fast the overall reaction takes place. Okay, if you're going on a hike with 10 people and you determine that you all have to stay together for safety reasons, everybody has to stay together, then the group can't walk any faster than the slowest person. If the group's going to stay together, the slowest person's going to determine how fast the group can walk, okay? And that's what's happening here as well. All right, so predict the rate law. So we said that the rate law is going to be, as long as the rate law includes reactants that are in the final overall equation, then the rate, the slowest step is going to determine the rate law. The rate law of the slowest step is going to be the rate law of the overall equation. So, in our overall equation, we have H2O2. That's the only compound in the reactants, and that does appear in the first, in the reactant side of the slow step. So that means this is going to be the rate law. Okay, so there will be the rate law because that is the rate law for the slowest step. So that will be the rate law for the overall equation. Now we should add one more thing that's not asked here. What is I minus? I minus is a catalyst. Okay, it appears at the beginning of the reaction, it speeds up the reaction, and it appears at the end of the reaction. When we did our elephant toothpaste reaction, we used yeast, which has a catalyst called catalase. We also could have used potassium iodide, Ki, which if you wanted to write it in the overall reaction, you could have written it up here, Ki. As you know, K, with your solubility rules, go back to your solubility rules, K will dissolve with anything and produce a potassium ion and an iodide ion. And the iodide ion does act as a catalyst for this type of reaction. I've used it in the past in class. We didn't use it this time, though. Okay, so that's a catalyst. It appears at the beginning. It appears at the end. It's not consumed or changed in the reaction. So let's just write that as a note here. I minus. Okay, so let's just finish up. So this is the rate law That's the rate law of the slow step, this, and of the overall reaction, this, okay? And really should just put the I minus there. It could be potassium iodide, but it's really the iodide ion that is the minus. So remember, in order for the rate law of the slowest step to actually be the rate law of the overall reaction, it can only contain reactants in the slow step that actually occur in the overall reaction here. And there you have the H2O2, and there you have the I minus, okay? If something appears in the rate law of the slow step that is not in the overall, that is not in the reactants of the overall reaction, you have to do some work, okay? And we did that problem in the lecture video. So that's the last 15 minutes of the lecture video. Okay, let's move on. Okay, and we're going to move on to our final problem in this assignment, 1474. So it's that NO catalyzes the decomposition of N2O, possibly by the following mechanism. And there you have the two steps. So what is the chemical equation for the overall reaction? Show how the two steps can be added to give the overall equation. Okay, this is Hess's law material here. So we look for something that only appears once anywhere, O2. And it's on the right side of the arrow, so we're going to write it over here. Okay, we put a box around it, means we've used it. What else do we have? We have NO and NO there. We have N2O. And N2O only appears over here on the left side. So we're going to put our arrow right about here. And we're going to put N2O here. Okay, so we've taken care of those two. Now, what else? We have N2 that only appears once, and it's right there, and it's on the right side of the arrow. So we're going to put that right here. Like that. Okay, and now we have 2 NO on the right and 1 NO on the left. So you're going to say 2 NO minus 1 NO. That leaves 1 NO, and it's going to be on the side with the bigger of the two numbers, the 2 side, okay? So that's going to put an NO over on this side, an NO over on this side. So we've taken care of these two. Okay, and finally we're left with 2 NO2 on this side and 1 NO2 on this side. So again, you subtract 2 NO2 minus 1 NO2 equals 1 NO2, and it goes over on the bigger side over on this side. Okay, and that would be the overall reaction, just the same way we did it with Hess's law. Let's just check our work. We got an O2 there, N2 there. Okay, let's go ahead and put the box around these since we finished with these. We've got the N2O. It doesn't appear anywhere else, so it's on the left side. 2NO minus NO gives you NO, and it's going to be on the right side. And 2NO2 minus NO2 is NO2, and that's going to appear on the left side. Okay, so there is our overall reaction. So we did A. B, why is NO considered a catalyst and not an intermediate? Well, very simply, it appears at the beginning of the first reaction, and it appears, although you have 2 in front of it, that doesn't change the fact it's still NO. It appears at the end of the final reaction. It did not get changed by the reaction. So catalyst appears at the beginning, it appears at the end, and does not get changed in the reaction. Let's go ahead and write that down. Okay, so a catalyst such as NO appears at the beginning of step 1 and at the end of the final step. In this case, that would be step 2. A catalyst is unchanged by the reaction. And what a catalyst does is catalyst speeds the reaction by lowering the activation energy. Okay, so there's your complete answer. Okay, in part C, the final part. If experiments show that during the decomposition of N2O and NO2, that at the end, let me reread that. If experiments show that during the decomposition of N2O, NO2 does not accumulate in measurable quantities, does this rule out the proposed mechanism? If you think not, suggest what might be going on. So it's saying that if during this reaction you don't have NO2 accumulating, building up, does that rule out that this is a possibility? And the answer is absolutely not. It just says that this is the slow step, just like in the problem before. If this is not accumulating, it means as soon as this is being produced by step 1, it's being gobbled up. It's being consumed by step 2, which would be the fast step. So as long as step 1 is the slow step and step 2 is the fast step, then no, you would not expect NO2 to be building up. If this were the fast step and you were producing this very quickly, and the second step were the slow step, then a lot of this would be sitting around. Remember, we said when we said that 3 things can happen if this were the fast step and this were being produced quickly. Either it can go down to the step 2, or it can go backwards. This would have to be a reversible reaction. It could go backwards to the reactants over here, or it could just sit there in solution as NO2. Those are the 3 things that could happen. That's if this was the fast step and this was a slow step. But if as long as the first step is the slow step, this is being produced very slowly, it's immediately going to be gobbled up by the fast step and run through the rest of the reaction. So no, this does not rule out this as a proposed mechanism. So let's write that out as an explanation. Okay, so the fact that NO2 does not accumulate means just collect or build up, does not accumulate, does not rule out the proposed rate mechanism. In other words, this. If the first step is the slow step, as we said up here, then the second step, the fast step, will consume the NO2. It'll go from here down to here as soon as it's produced. And there will be no accumulation of NO2 in solution. Okay, so the answer is no, it does not rule out the proposed mechanism. So by the way, this is the way you would want to write an AP answer. Okay, you want to state your answer right up front. Don't get into all the reasoning at first and then leave the final answer for the end. Just start off stating this at the beginning. The fact that NO2 does not accumulate does not rule out the proposed mechanism. Bam, that's the answer to the question. Be sure you write your answers in that form. Okay, that takes care of this lesson of the answers video for this particular Day 50 lesson, and we'll see you on the next lesson.